Good morning, students. Today we'll be learning our next theory, that is valence bond theory. Now, students, we have learned the covalent bond formation from class 10th. We have seen the molecules of F2, N2, O2, H2. Okay, other molecules like NH3, water, methane, these all formations of covalent bondings you have just seen from 10th onwards. So you know that there is a covalent bond formation whenever there is the sharing of electrons. Now sharing of electrons means that when there is a requirement of two electrons, one atom will be giving us one electron, the other atom will be giving us another electron in the common electron cloud, and then there is a formation of covalent bond. Now in this valence bond theory, we'll go deep into how covalent bond formations are there actually. Okay, more deeper than what we have learned before. And we'll be also helping us to find out the cause of the covalent bond formation and different amount of energy which is released during the different formation of molecules. Those things we can just predict out from this theory. Now this theory is very simple. Please understand those. Firstly, this theory was proposed by Hitler and London in 1927. But then it was extended, it was more extended by Pauling and Slater in 1931. Now let us know about the main postulates of this theory. The first postulate is that a covalent bond is formed by the overlapping of atomic orbitals which is present in the valence shell of the two atoms. Till now we were seeing that it is due to the electrons coming into the electron cloud from each atom. Now we have a concept of atomic orbitals with us, which you have learnt in second chapter, atomic orbitals, s orbital, p orbitals, d and f orbitals. So this theory is telling us that it's due to the overlapping of atomic orbitals which is responsible actually for the covalent bond formation. Of course, the electrons are present in those atomic orbitals. Now the next theory, next postulate, not the theory, next postulate is saying us that only half-filled atomic orbitals, that is the orbitals which will have a single electron with it, can enter into this overlapping process. Now when those two atoms with two different orbitals, as I have shown you here, comes with single electrons each, then there is a formation of this molecular orbital which has two electrons with opposite spin. Now this is the covalent bond formation here. Okay, you can see the spins are varying of the two atomic orbitals which is coming for the overlapping purpose. If they overlap, they'll form molecular orbital. Molecular orbital you'll be learning later also. So now there is a formation of covalent bond. Now the third postulate says us that the atoms with half-filled orbitals must come closer to one another with their axes in proper directions for overlapping. Now we know that p orbital is a dumbbell shaped. Okay, and it is cylindrical also. We also know that we have three types of orbitals, px, py, pz. Those you would be telling me. And the another thing is that please understand that these are electron clouds. So one of the lobe of p orbital is in phase, we say in phase, that is used for constructive interference, and the other lobe is out of phase, that is for destructive interference. Now there are some symmetrical as well as asymmetrical overlapping which can happen. Now only the symmetrical overlapping will give you the covalent bond formation. Asymmetrical overlapping won't give you any covalent bond, won't be formed actually. Okay, the symmetrical, when we see the overlapping, what does that mean? Suppose a p orbital is in this way. Okay, this is in phase lobe and this is out of phase lobe. Okay, now another p orbital comes into play, where this is the plus lobe and this is the minus lobe. So what happens is, this plus you can see, so there will be a covalent bond formation because this is symmetrical. This is symmetrical, okay? Both are in phase. This is symmetrical. So there will be a covalent bond formation. Now for the second one, suppose we have it in this way. This can also happen as well. Suppose this minus lobe is towards this side, and the other one which is coming for bond formation, that is also having a minus lobe towards this side only. So that is also again symmetrical. Whether it is in phase or out of phase, in both the cases, those are symmetrical. But if this happens, that the plus lobe of one of the p orbital is towards the overlapping side, and another orbital which is coming for overlapping, that has a minus lobe towards this side. Now that becomes asymmetrical. Okay, one of them is in phase and another is out of phase, so that becomes asymmetrical, and there will be no covalent bond formation for this one. Okay, so the next postulates, if any. Okay, I'm left with some of the postulates here itself. The fourth postulate is saying that maximum electron density is there in the overlapping region. As you can see here, maximum density is over here, so the lobe is little thicker in between, as I've shown you here. And the next one is that greater will be the overlapping, and higher will be the strength of the chemical bond. This is what the postulate says. Because more energy will be released, greater the overlapping, amount of energy released per mole will be more, and we know that strengthens the bond. Okay, that stabilizes the system. The sixth one is that electrons which are paired in the valency shell can jump to higher orbitals, thus forming orbitals with unpaired electrons. What does that mean? For suppose we have the formation of CH4. Now carbon in the ground state, what is its configuration? Configuration goes in this way. I'll write it smaller. So it is 2s2 and 2p2. Okay, so in this way it is, right? But when we talk about CH4 bond formation, then we need to have 4 such unpaired electron orbitals. That is, you have only 2 orbitals over here in the ground state, which are with unpaired electrons. But as we can see in this theory, what it tells us, there will be a bond formation only when you have orbitals with unpaired electrons, that is 1 electron. So in that case, you need to have 4 such orbitals which will have unpaired only 1 electron with it. So for that, what you can do, you can just shift one of the electron, or you can say that an electron from the s orbital will be jumping to the p orbital in the excited state, thus giving us C. Here 1 will be left in the 2s orbital side, and 2x, 2p, it was already there, and 2pz now, because one of the electron from the s orbital has jumped to the p orbital. So now how many you get? You get 4 such unpaired electrons. 4 such orbitals where you have only one electron. So that can go for covalent bond formation. Okay, that has been explained by the 6th postulate over here. Next we go for some other topics. Now the next topic is that, see, whenever this bond formation happens, or covalent bond overlapping is there, or you can say simply overlapping is there, we can have 2 types of bond with us. One is sigma bond, the other one is pi bond. Sigma bond can also be written in this way. Okay, so please remember that sigma bonds are formed only when there is an overlapping of singly occupied orbitals along their axis. That is end-to-end overlap, or head-on overlap we call. Okay, one is head-on overlap. For pi bond, we will be seeing sidewise overlap. So this is head-on overlap. Okay. So whenever the bond orbital which is symmetrical about the line joining the 2 nuclei, those type of orbitals will be the sigma ones. Okay, and it is formed by head-on overlap or end-to-end overlap. We call it end-to-end overlap or head-on overlap. So this is how it is going to be. Now we'll be seeing the examples and also the formations. The first one where we can see a sigma bond formation is SS overlapping. That is, two s orbitals will come into play. So for that, the best example would be H2 molecule, where we can have, see, suppose for one H atom we have one s orbital with the spin, the electron having one of the spin. Okay, now for the other H atom we have other spin opposite to each other. Now when this comes together, see, the two s orbitals approaches towards each other, have an overlap, head-on overlap. Okay, we know s orbital is spherical and it is symmetrical. So when both the 1s orbitals of both the hydrogen atoms approaches each other, they come closer, and when there is a maximum attraction of the two nuclei, they overlap and form a sigma bond. As you can see here, I have shown the electrons like this, okay, with opposite spins. And now you have a molecular orbital where you have more of electron density in between. Molecular orbital you'll be knowing later in details, okay. Now next go for the, so I hope that this SS overlapping is clear to you. Both the atoms with s orbitals are coming closer to each other and forming a sigma bond, which is, we are calling it as SS overlapping. Now for the next one, we'll take an example of sp overlapping. This is a sp overlapping. Okay, so you can understand from the name itself that there is a s orbital coming into play and there is a p orbital coming into play. For example, we'll take an example of HF molecule, where we can clearly observe the sp overlapping. Now for this case, suppose H atom is with a s orbital over here. It has come with a s orbital, of course one s orbital. Now F atom, what do we know about F atom's orbital configuration? We know it is 1s2, like you can see over here, 2s2, this is also there, and 2p5. So 2p5, when we write this, suppose it is px, okay, and this is py and pz. When you draw that 5, so you put singly first and then you pair it up. So we can see that px and py is paired and pz is left. Okay. Now pz we can show it in this way, s orbital. See, you can see the opposite spins. Suppose s orbital is having this spin, p orbital will be having the opposite spin. Now as this is a head-on overlap, see, the axis towards this side and the axis is here. So this axis can easily overlap. So you can see the overlapping region where you can find two electrons. And thus, here the electron density is more. I told you the overlapping region will have a greater electron density, which means the lobe is now a much bigger one, you can see. After the formation, this lobe will grow, and so this is looking into a smaller one. Okay, this is how there is a formation of sp overlapping. Or in the case of HF molecule, nothing like one s orbital from H is coming into play and one pz orbital from F is coming into play, forming a bond, that is a sigma bond. Okay. Now there is also bond formations with water molecule, which you can show it. I'll just tell you in short the water molecule bond formation. How can it be? Like, see, when you draw a water molecule, we have a central atom, oxygen, right? Now if we draw that oxygen p orbital, what do you get? 2s2 is there, 1s I am not writing it for oxygen. This is 2s, so it is 2s2 here, and the other one is 2p2, right? That is the bond formation, 1s2, 2s2, 2p2, of course. Okay. Now what happens here? Now, you have oxygen as a central element and you have 8 electrons in its outermost configuration. 8 electrons in its total. Okay, so 1s2, 2s2. This gives you 4 and 2p 4. Now this is 3 and this is 4. Now suppose this is px and this is py and this is pz. Okay. So what happens now? You have two such orbitals which is unpaired here. Now with that, what you have to do? Suppose I draw that py and pz orbitals. I draw it here. Pz and this is py. Suppose this is py and this is pz. Suppose, okay. So you have this type of two orbitals which can combine with two s orbitals. Here you get two hydrogen atoms. From there you will get two orbitals, s orbitals. Okay. So this is one s orbital of one hydrogen atom. This is one s orbital of another hydrogen atom. So this will combine. Here this will combine with a bond formation will happen. Here this will combine, a bond formation will happen. Another thing, here there will be a spin and here there will be an opposite spin. Here there will be a spin, here there will be an opposite spin. Okay. So in the next step, I'll try to write it shortly. Like this will bond formation in this way, right? This is your bond formation for water molecule in case of valence bond theory. Similarly, I hope that you will be able to show me in this way only the ammonia bond formation in a similar way. Like you write the electronic configuration, find out the orbitals which are going for covalent bond formation. Like I have found that py and pz will be going on to play. So I have drawn the py and pz, and I know that it will overlap with two such hydrogen atoms because H2O, right? So in that case I have drawn it. So in that way you just try for ammonia molecule. If you are able to, it's very good. If you are not able, then I'll tell you. So I hope that is clear to you that in the case of HF molecule, what I told, this s orbital is going for the bond formation with this pz orbital. Okay, nothing more into this. Next part I'll go. Next part is, okay, another type of overlapping for the sigma bond can happen, that is pp overlapping. How does this happen? We can take an example of F2 molecule over here. pp orbital overlapping means you can understand that you need two such atoms which are giving you p orbitals. Okay. Now for if we write the electronic configuration, let me write it first. 1s2, this is 2s2, and this is, okay, so 9 in total, right? 5. Okay. So now what would happen? Let me write, I won't write this 1s, I would write only 2s and 2p. That would be fine. Okay. Now 2s, this is 2s. Okay. This is 2s, 2p. Now 5, singly occupied. And then I'm doubly making it. So this is my px, py, and this is my pz. So one of the orbital I am getting where it is unpaired electron. Okay. pz, that is. This is for another f atom where this is my 2s. So 2 electrons, similar. And this is my 2p. Okay. Now this is my px. Please understand. Py and pz. Just for understanding purpose, I have just made it into this way. Px, from px we start 5. 1, 2, 3, 4, 5. So pz is again left. So in both the atoms, pz orbitals are left with 1 electrons. So that can overlap obviously. Okay. So the pz orbital overlapping. So this is one of the spin. This is the opposite spin going on to play. And as you can see here, the overlapping. So this is the thing, electrons over here. And this gets into more density. So the lobe becomes larger. So this is the way sigma molecular orbital is formed. Okay. So this is the way where what we are seeing in the sigma bond, we are seeing SS overlapping, we are seeing SP overlapping, and as well as that we are seeing the PP overlapping as well. PP overlapping, in the case of PP overlapping, of course, p orbitals will be involved in both the atoms. okay, and it should be an head-on overlap. Then only the covalent bond formation will happen. Now let us go for pi orbitals. How does this pi orbital forms? This is because of the sidewise overlapping, or you can say lateral overlapping. That was head-on overlapping. This is sidewise overlapping. Okay, that was end-to-end overlapping. This is lateral overlapping. Now this overlapping will take place at the side of the two lobes, and hence the extent of the overlapping, as you can see here, is relatively smaller. So you can say that pi bond is relatively weaker as compared to the sigma bond. It was a head-on overlap. This is a sidewise overlap. Okay, and the molecular orbital will be oriented above and below the plane, as you can see over here in the picture. Now let us go for an example where we'll be clearly understanding about the pi bond formation. Okay, we'll take an example of oxygen molecule. So in case of oxygen molecule, suppose I write the oxygen molecule's electronic configuration. 1s2, 2s2, and this is 2p4. Okay. Now, in the case of 1s2, 2s2, 2p4, what we can see the electronic configuration as, we'll write only s, 2s and 2p's over here. Okay. 2s is 2s2. This is the way. Okay. And then it is 2p4. Okay. 1, 2, 3, and 4. This is px, py, and pz. Another oxygen atom also comes in this way, so I just write it. Now see, for better understanding, I just have written px on this side, py on this side, and pz on this side. So I will fill up in this way only, and this. Okay. So we can get two such orbitals from each atoms where you have only single electrons. So those will go into the bond formation. Now I have just drawn it in this way for the two orbitals. We know px is completely filled, so it won't go for covalent bond formation. Py and pz will go, so I have just drawn the lobes in this way, and see how this is going on. This would come closer, so you have here a single electron, opposite spin electron over here, a single electron here, and opposite spin over here, suppose. Okay, and so this is the bond formation. One will come with an head-on overlap where you will be forming a sigma bond, and the other one will be coming as a sidewise overlap. It will get closer. Okay, it's not shown because we have seen that the pi bondings, in case of pi bonding, these and this bonds, okay, come to still smaller, but it comes to an overlapping extent. Okay, so that will overlap and it will give you a sidewise overlapping, forming a pi bond. So this will be the molecular orbital formation. So this is what we have learned for pi orbitals, sigma orbitals. Sigma, in case of sigma bondings, we have seen three types of overlapping: SS overlapping, SP overlapping, and PP overlapping. But in the case of pi bond, we are just seeing bonding which is formed a sidewise overlapping of orbitals, and it will only include PP overlapping. P orbitals only include, there is no consideration of S orbitals here. There will be a pi bond formation only with the P orbitals, and this pi bond will be formed after the formation of a sigma bond. Where there is no formation of a sigma bond, how can this pi bond come into play? Whenever this comes into play, you can see that there is a formation of sigma bond first, because these two orbitals will come into play. They will overlap, and then there will be a sidewise overlapping of these two orbitals. Okay, so that is there. And also we have learned that sigma bond will be a stronger bond, and pi bond will be a weaker bond, because that was a head-on overlap, symmetrical along the axes. But for the pi bond, we have seen that it's a relatively weaker one, because the overlapping takes place at the side of the two lobes. Okay, so and And also, in case of sigma bond, there will be a free rotation of atoms around this bond because it's a symmetrical one. But free rotation is not possible with the pi bond, because then that will break up. Okay, that will break. So these are the few comparisons between the sigma and the pi bonds. Rest you will also find out from your book. You find out from there. It will be very beneficial for you. It's an important one. Okay. So I'm just for the next video I'll just tell you what will be the next one. Also, I have told you something to find out in the video. While overlapping, I have told you to find some of the molecules overlapping to show me that you do.